Okay, now what we're going to look at is a situation where we have more than two groups. We have to use a different type of test for that. Just as a refresher, we have some t-tests that are used for two groups. And there's two different ways we can do that. One is where we have one group with two tests, or what's called a dependent or paired t-test. And we have one group called a independent test where we have two different groups compared on one score. And within both of those, we have something called one-tailed and two-tailed test. One-tailed meaning that we think that one score is going to be higher than the other. For example, we might say that the GRE scores of women are higher than that of men. Or we could have a two-tailed test and say simply that we think there's a difference in the GRE scores of men and women, but we're not sure where it is, and we're willing to leave the door open to two possibilities. Questions often asked, can we do multiple t-tests? You can, as long as those multiple t-tests are on different measures. However, you cannot compare freshmen to sophomores to juniors because you're running up multiple t-tests on the same group and it creates error. So to show you an example, and I've included this in your materials. This is a situation where we want to know how long it takes somebody to tie a bow on their shoes, where some were using with their thumbs and some without their thumbs, and we have the time allowed for each of the people to do that. So here's a situation where we have a paired t-test in which each person is allowed to tie a bow with their thumbs and without their thumbs, and we have a set of scores on each one. We have an average time, the median time, and the standard deviation for those. And we can compare how those people did, and we can see that there is a significant difference, alpha level of 0.05, between the time with the thumbs and the time without the thumbs. So here's a real brief example of a paired samples t-test where we are comparing one group two different times, and we can say there's a significant difference in the mean scores of those two groups. Okay, let's consider this situation. Let's suppose I'm interested in comparing the freshmen and sophomores in regard to PSAT scores. If I wanted to do that, I could do an independent sample t-test, take all the scores of the freshmen and all the scores of the sophomores, and compare them and see if there's a significant difference. That'd be an independent sample t-test. However, what if I wanted to compare the scores of the freshmen to the scores of the sophomores, to the scores of the juniors, to the scores of the seniors? I can't do that with the same test, because if I compared freshman to sophomore, sophomore to junior, junior to senior, sophomore to senior, juniors to freshmen, seniors to freshmen, I'd have, every time I did a test, I'd have error. Well, you can see that if you were to do that over and over, that'd be a lot of error that would be calculated into that, and you wouldn't find out anything. So the way around that is to do something called a one-way ANOVA. It is used for a very specific purpose. We're using this when we have one independent variable, at least for now, what we're going to stick with is one independent variable, that which we can control or manipulate, and one dependent variable, that value that may be determined by the independent variable. So, if I was interested in studying PSAT scores among all levels in high school, we could make a chart that would show the representation of that, and it would look something like this. Have a classification, have freshman, sophomore, junior, and senior, and the scores on the PSAT. So the mean score for freshmen is 700, sophomores is 720, juniors is 800, seniors is 820. And what I want to know is, does their classification make a difference, or is a difference in their mean scores? So I've got an independent variable and a dependent variable. So the variable I'm allowing to fluctuate is their freshman, sophomore, junior, or senior status. The dependent variable, what I want to know is, does this classification make a difference on their score? I can't really control what their scores are. But what I can look at or allow to fluctuate is what their classification is. So this is the independent variable. This is the dependent variable. And I also put another document in your Chapter 10 materials, I think it's Chapter 10 or 11, to explain some other differences between independent and dependent variables. And I have different groups: freshmen, sophomores, juniors, and seniors. Now, it is possible that there is some differences in scores within each group. Obviously, not every freshman is going to get a 700. So there is some difference within each of those four groups, within the freshmen, within the sophomores, within the juniors, within the seniors. What we want to know is the difference between freshmen, sophomores, juniors, and seniors greater than the difference within each of those groups. And this creates a ratio, and it gives us some information. One of the things is called an F-score, and we also get a p-value. Now, what we want to know, or what our null hypothesis would be, is that the mean score of freshmen is equal to the mean score of sophomores, is equal to the mean score of juniors, is equal to the mean score of seniors. Now, if I determine that any part of that equation is not true, then I can reject my null hypothesis. When you look at an ANOVA table, you'll see a great deal of information. So here's an example. This is a situation, and you should have this in your stuff as well, where a researcher wanted to know if a person's age influenced how they view polls. So if I look at this, one of the questions it asks is, how many groups do I have? Well, between groups, the degree of freedom is 6, and this works just like the other situation. I add 1 to that, so I had 7 different age groups. And I've got people within those groups. And what this does is it takes one person away from each group to determine the degree of freedom. So my total participants in this is 1,438, because there's one person put back in for each group and one for the total as well. This part in the middle you don't really need to worry about. Really, even this F-score you don't need to worry about either. What we want to know is there is a significant difference between the groups. If this number is less than 0.05, then that means that there is a significant difference between the groups, between the age groups in this situation, that the difference between them is greater than the difference within them. This part that's within group down here is also referred to as error or residual. You'll see that from time to time. Another way you might see this same information is the perception of polls differs significantly depending on the age of respondents. And you can see where this degree of freedom came from. You can see where each of these numbers came from. The 6 on the degree of freedom is this 6 in this table. It's 1,431 is this number. This is your F-score. This is the computer, the calculation taken from the computer. You don't have to figure that out, but it'll give you an F-score. And really, what you're looking for is the significance of 0.001, or less than 0.05, and in this case it is. So there's 2 different ways you'll see this done. One in the tables, one in a sentence like that.